Welcome to the Deep Dive, where we cut through the noise and get straight to the insights. Today, we're plunging into a field that's, well, it's buzzing with incredible potential. Deep learning. You've probably heard how it's transformed everything from healthcare to entertainment. But for our deep dive today, we're zeroing in on a particularly vital area, how this, cutting edge tech is really impacting ecology and conservation. Our mission is kind of like deep learning in ecology, separating fact from hype.
hmm
We want to give you a balanced, critical look, but a constructive one too. What can deep learning actually do here? Where does it maybe fall short? And crucially, how can we use it responsibly? Maximize the benefits, avoid the pitfalls. Because the fascinating thing is, ecology provides these vast data streams, images, audio, satellite data. It all seems perfectly suited for deep learning's pattern recognition, right?
Exactly. It seems like a perfect match on the surface.
But, as we'll get into, the unique challenges with ecological data mean it's not always that straightforward. Okay, let's maybe unpack this a bit. Deep learning itself. We're talking about layered neural networks, right? Basically complex computer programs designed to learn intricate patterns from data.
That's the core idea, yeah. Layers processing information at different levels of abstraction.
And ecology feels like such a promising field for this, like you said, because of those huge, diverse data streams. I mean, imagine trying to manually ID every animal in thousands of camera trap photos, or every bird call in hours of audio.
Oh, absolutely. The sheer volume, it
Yeah.
just screams for automation. But what's really fascinating here and kind of the crux of the issue is the difference between the data deep learning often sees in tech and ecological data.
Okay, how so?
Well, unlike, say, curated online image libraries, ecological data is often different,
Yeah.
significantly different. It could be scarce, maybe not enough examples of a rare species. It's often noisy, think bad weather in photos, wind and audio. It can be biased, depending on how or where you collected it. And it's super context sensitive,
Meaning.
meaning what a model learns in one forest might just not apply in another. Different conditions, different
Mhm.
species interactions. So that immediately sets the stage for both the potential and the very real challenges these models face out there.
Okay, so given these quirks, the noise, the scarcity, the context thing, does that mean ecologists are using like totally different deep learning tools, or are they adapting the common ones?
That's a great question. It's mostly about adaptation, but also using the right tool for the job.
Yeah.
You definitely have the powerhouses like convolutional neural networks, CNNs. They're specialized for image tasks, recognizing animals in photos, mapping habitats from satellite images, that sort of thing.
Right, the visual stuff.
Exactly.
Yeah.
But ecologists are definitely adapting them and using others too, like recurrent models and newer ones like transformers. They're really good for sequences.
Just sequences like animal movement or
Yeah.
sound patterns.
Precisely. Think patterns over time. Tracking animal movement from GPS tags, analyzing the structure of a bird song, even genetic sequences, they have this memory component, which is key for time-dependent data.
So it's less a fixed toolbox, more like a versatile toolkit needing adjustments. Interesting. What else is in there?
Well, there's growing interest in graph neural networks, GNNs.
Okay, what are they good for?
Think ecological networks. Food webs, species interactions. GNNs are designed to understand relationships and connections within a system. So not just identifying what species are there, but maybe how they're interacting.
Mapping the connections.
Yeah.
Neat.
And then you have generative models.
Yeah.
These are interesting because they can create new data that looks real
Why would you do that?
for data augmentation. If you have very few examples of something rare, you can sometimes use these models to generate more synthetic but realistic examples to help train your main model better. It helps when real labeled data is scarce.
Okay, that generative part is clever. But it brings up a really critical question. What do ecologists need to actually do to make these sophisticated methods work effectively? It's clearly not just picking a model off the shelf, is it?
Absolutely not. It's
Yeah.
so much about the groundwork, the preparation. You need high-quality labeled data. That's foundational. Garbage in, garbage out.
Right. The labels have to be accurate.
Exactly. And you need to carefully handle sampling bias. Is your data truly representative, or did you just sample near roads, for example? Effective data augmentation, like we just mentioned. Transfer learning is also huge.
What's transfer learning again?
It's where you take a model that's already been trained on a massive general data set, like millions of internet images, and then you fine-tune it on your specific, smaller ecological data set. It gives you a head start.
Okay, leverage existing knowledge.
Precisely.
Yeah.
And finally, robust evaluation. Critically, this includes uncertainty quantification.
So the model telling you how sure it is.
Exactly. Like, I'm 90% sure this is a deer, but only 50% sure about that blurry thing in the corner. That's vital for making real-world conservation decisions. You need to know the confidence level.
All right, so we've got the what deep learning basics and the why its potential in ecology, plus the data challenges. But I think for a lot of listeners, the real question is, okay, what does this actually look like right now? Can we talk about some concrete examples? Where is deep learning making a difference? And maybe where is it still, hitting some walls?
Yeah, definitely.
Yeah.
Let's take camera trap classification. This is a big one. Automating species ID in those millions of photos saves conservationists just enormous amounts of time.
I can imagine.
But the pitfalls are real. They often struggle with rare species, not enough training examples, and generalization is tough. A model trained really well in, say, a rainforest in Costa Rica might perform poorly in a savanna in Kenya. Different lighting, different backgrounds, maybe slightly different animal poses.
Oh, like that leopard example you mentioned earlier, classifying shadows.
Exactly that kind of thing. It highlights that these models aren't magic. They learn patterns from the data they see. If the new data looks different, they can get confused. It's a powerful tool, but not yet a universally applicable one without careful work.
That really drives home those in the wild challenges. Okay, what else? Acoustic monitoring.
Acoustic monitoring, yeah. Also huge. It's incredibly effective for species with really distinctive calls, certain frogs, birds, bats.
Things you can easily pick out.
Exactly.
Yeah.
But it gets much harder with background noise, winds, rain, other animals, and overlapping calls, like a whole chorus of frogs calling at once. Trying to separate those individual signals is technically very challenging.
Right, the signal to noise problem.
Precisely. Then there's remote sensing for habitat mapping. Deep learning can produce these amazingly high-resolution maps showing deforestation or habitat recovery.
Yeah.
It's revolutionary for tracking landscape change.
That sounds incredibly powerful.
It is. But again, generalization issues pop up. A model trained on satellite images from one type of sensor or during one season might not work well with images from a different sensor or taken during a different time of year when the vegetation looks different.
Different eyes in the sky, different seasons. More context issues.
Exactly. Individual identification, like recognizing specific whales by their fluke patterns or primates by their faces, using pose estimation that works, sometimes remarkably well. But it typically needs a lot of training data, many photos or videos of the same individuals.
Okay, data hungry for that one.
Very. And finally, species distribution modeling. Deep learning can model really complex relationships between species presence and environmental factors. It can help predict where species might live now or where they might move under climate change.
Potentially very useful for conservation planning.
Immensely. But the ecological plausibility needs constant checking by human experts. Does the predicted map actually make biological sense? Or is the model just finding some weird statistical fluke?
Okay, so it's clear across the board. Powerful potential, but definitely not a magic wand. There are consistent hurdles. If we zoom out a bit, connecting this to the bigger picture, what are some of the really general limitations or common ways these deep learning models fail in ecology?
Yeah, stepping back, there are several recurring themes. One is overconfident predictions. A model might be wrong, but still report very high confidence. That's dangerous.
Right, misplaced certainty.
Another is spurious correlations. The model learns a pattern that exists in the training data but isn't ecologically meaningful. Like maybe it associates a rare plant only with photos taken on Tuesdays just by chance in the data collection schedule.
Uh-oh.
Poor generalization is the big one we keep hitting. The model works in its training environment but fails when conditions change slightly. It hasn't learned the underlying ecological rules, just superficial patterns.
The context dependency again.
Exactly. And data biases are baked in. If your camera traps were mostly placed along trails, your model might get really good at identifying trail-using animals, but be terrible at identifying species that avoid trails. The model reflects the bias in the data collection.
Makes sense.
Crucially, they often lack causal insight. They're great at finding correlations. Species X is often found near river Y, but they usually can't tell you why. Is it the water? The vegetation near the water? Something else entirely. They don't understand cause and effect.
Just pattern matchers, fundamentally.
In essence, yes. And then there are practical issues, like reproducibility. Sometimes it's hard for other researchers to get the exact same results, which is a concern for scientific rigor. Privacy risks, too, especially if data involves human activity or sensitive locations.
So the technical hurdles are clear and pretty significant. But are there broader issues beyond just the algorithms? Maybe societal or ethical things ecologists need to think about when using these tools?
Oh, absolutely. That's a critical layer. We have to talk about the ethical, legal, and social implications, often called ELSI.
ELSI, okay. What falls under that?
Well, there are serious risks, for instance, of inadvertently aiding exploitation. If a tool becomes too good at locating rare species, could that information fall into the wrong hands, like poachers?
Wow, yeah, that's a scary thought.
It is. Then there's intellectual property and community rights. A lot of ecological data is collected on indigenous lands or involves local knowledge. Who owns that data? How are benefits shared? These are complex questions with no easy answers.
Hmm. Data sovereignty.
Exactly. There are also potential workforce impacts. Will these tools displace human ecologists or field technicians? Or will they augment their skills and free them up for higher-level tasks? It's probably a mix, but needs consideration.
The human element.
And finally, just basic legal compliance. Are data collection and use compliant with wildlife protection laws, data privacy regulations like GDPR, and so on? It's not just about good science. It's about responsible and legal practice.
Okay, so factoring in the tech challenges and these critical ELSI considerations, it sounds complex. How can ecologists actually use deep learning effectively and responsibly? I know our source material laid out some practical guidelines.
Yes, it did. And they're really valuable. There are basically 9 key points. First, and maybe most importantly, start with a clear conservation question, not with the method.
Don't just use deep learning because it's cool.
Exactly. It sounds obvious, right? Yeah. But it's a common pitfall.
Why do you think that happens so often? Teams get excited about the tech.
Partly, yeah. The tech is exciting, but without a really specific ecological or conservation question driving the project, like how is livestock grazing impacting snow leopard prey density in this specific valley? Or can we detect invasive species X early using drone imagery? You risk doing technically impressive work that doesn't actually lead to an actionable conservation outcome.
You end up with a fancy model, but no real answer to a problem.
Precisely. You might generate amazing data analysis, but if it wasn't designed to answer a concrete question relevant to management or policy, it just sits there. So, question first.
Got it. Crystal clear question first. What's guideline number 2?
Second, rigorously assess your data quality and quantity. Know its limitations.
Okay. Understand your ingredients.
Third, always use simpler models as baselines. Don't jump straight to the most complex deep learning model. See if a simpler statistical method works reasonably well first. Then you know if the complexity is actually buying you anything.
Benchmark it. Makes sense.
Fourth, validate models with spatial temporal awareness. Check if it works in different places and at different times, not just on data withheld from the same location and time period.
Testing that generalization properly.
Fifth, quantify uncertainty. We talked about the know how confident the model is.
Right. Number 6.
Sixth, plan for long-term model maintenance. Models aren't static. The environment changes, data drifts. They need updates and monitoring. It's not a one-and-done thing.
Like maintaining any important tool.
Seventh, document everything thoroughly. The code, the methods, the data processing steps. For transparency and reproducibility.
Good science practice.
Eighth, engage stakeholders early and often. This includes local communities, land managers, policymakers. Ensure the tool is actually useful and usable for the people who need it. And address those ELSI concerns proactively.
Bring people along.
And ninth, consider combining deep learning with mechanistic models. These are models based on ecological theory and first principles. Combining data-driven deep learning with theory-driven models can give you deeper insights than either could alone.
Okay, that's a solid checklist for doing this responsibly now. But what about the future? What's on the horizon? Where does deep learning in ecology go next? This is where it gets really interesting, right?
Yeah, the future directions are genuinely exciting. We're seeing much more work on Bayesian deep learning and other uncertainty-aware models. Getting better handles on model confidence is a major push.
Making them less like black boxes about their own certainty.
Exactly. Self-supervised learning is another huge area. This aims to reduce the bottleneck of needing vast amounts of labeled data. Models learn useful representations from unlabeled data, which ecology has in abundance.
Learning from the raw stuff, that could be a game changer.
Potentially, yes. Then there are those hybrid mechanistic data models we just mentioned, really trying to integrate ecological understanding into the AI. Not just pattern matching, but encoding some ecological rules.
Best of both worlds.
That's the goal. Federated learning is also emerging for privacy.
How does that work?
It allows multiple organizations to train a shared model on their local data without ever sharing the raw data itself. Only model updates are exchanged. Think hospitals collaborating on medical AI without sharing patient records. Same principle could apply to sensitive conservation data across different parks or countries.
Ah, collaborative learning without data exposure. Clever.
Yeah. We're also seeing pushes for standardized benchmarks, so we can compare models fairly across different studies, and more interpretable AI tools methods to help us understand why a model made a certain prediction, moving away from the black box problem.
Opening the box a bit.
Trying to, yeah. And finally, a very practical need. More energy-efficient models. Models that can run on low-power devices in the field, on drones or remote sensors, without needing massive computing resources or draining batteries instantly.
That's a lot of exciting potential. Okay, to make this even more concrete, let's touch on some real-world case studies where these kinds of approaches are actually being used. What stands out to you from those practical applications?
What's really compelling, I think, are the examples that show that careful, integrated approach we've been discussing. It's not just about the AI itself. For instance, you see large-scale camera trap projects like Snapshot Safari or Wildlife Insights. They use deep learning for initial sorting, but they build in iterative expert feedback loops. Human experts review the AI's uncertain classifications, and that feedback is used to continually retrain and improve the models.
So humans and AI working together, refining the system.
Exactly, it's a partnership. Similarly, in acoustic monitoring for birds or bats, you see hybrid human-AI workflows becoming common. The AI flags potential calls of interest in massive audio files, but then a human expert verifies the crucial detections before they're used for, say, endangered species monitoring.
AI does the heavy lifting, humans provide the critical check.
Precisely. For habitat change detection, people are successfully using cross-sensor retraining. They train a model on data from one satellite, then adapt it to work with data from a different satellite, overcoming some of those generalization issues we talked about by explicitly teaching the model to handle different data sources.
Adapting to new eyes, as you said.
Yeah. And in marine mammal identification, projects often integrate human-in-the-loop verification. The AI might suggest potential matches for individual whales based on fluke photos, but researchers confirm the match before it goes into the official population count. It builds trust and ensures accuracy for critical population estimates.
Okay, so the common thread seems to be integration AI isn't replacing ecologists, but augmenting them, and often requires that human expertise in the loop for validation and refinement.
That's exactly right. The most successful applications treat deep learning as a powerful tool within a broader ecological workflow, not as a standalone magic solution.
Right, so recapping here. Deep learning clearly offers significant, very real potential for ecology and conservation, but as we've explored, it's definitely not a magic bullet. Its greatest value seems to come when it's deeply embedded in sound ecological thinking, driven by clear conservation goals, backed up by careful validation, and this seems crucial involving stakeholders robustly.
Couldn't agree more. The tool is powerful, but how it's wielded and within what framework makes all the difference.
So maybe to leave you, our listener, with a final thought to mull over. How might this ongoing evolution of deep learning getting more interpretable, more context-aware, maybe better integrated with ecological theory, how might that fundamentally redefine our understanding of really complex ecosystems? And maybe even more excitingly, what new questions we couldn't even properly ask before will we be able to ask, and maybe even answer about the natural world thanks to these evolving tools? Something to think about.